Hi. A few years back I produced a short video for a friend of mine over in France. Jackie is his name. He lives near Vienne in France along the Rhone River. Not Vienna, but Vienne. And well, it had to do with offsetting a part in order to produce, well, in this case, a very small crankshaft. Now, I showed certain techniques in the video, but I've never made a crankshaft or shown how to make the crankshaft proper. So that's what we're going to be doing today. Now, if you want to get clued into what happened before, well, here's a link to that original video. So, as I said, the part is quite small, and if we look at our drawing here, we can see that we have our main diameter at 8 millimeters. That's not very big, and a length of what, about 4 millimeters. Now that is the centered diameter, and then we have two lobes, eccentric lobes here, that measure each 12 millimeters in diameter by, again, about 4 millimeters in length. So that'll be a total of 12 millimeters in length. Now, if we look at the eccentric lobes themselves, we can see that they're offset by 2 millimeters side to side of our main on this crankshaft. But it's not 2 millimeters X or Y. It's really 2 millimeters in both X and Y. And that means that what we have here is really the hypotenuse of a triangle. And we're going to have to do a little math to know how far to offset in one axis and how far to offset in the other to get that 2 millimeter distance center to center at a 30-degree angle. Now, to do that, we're going to have to do the math. And if you see that small triangle that shows up on our drawing here, from the center to one center of lobe, so center of the part to center of one of the lobes, well, if we look at that triangle and we cut it into a right angle triangle by drawing a line perpendicular from the center line down to that second point, well, we end up with this triangle here, and that, well, is the one that we have to resolve. So what I have here is a right angle triangle, 30 degrees, with a hypotenuse that is 2 millimeters long. And well, if I resolve the triangle, I end up with an opposite side to the angle of 1 millimeter and an adjacent side to that angle of 1.73205 millimeters. And that is way too accurate for a millimeter here, but we're going to go to that many decimals just to show that when we verify our calculations that it actually does work out. And how did I get to those answers? Well, with basic trigonometry. And if I look here, I have sine 30 degrees equals opposite over 2. Where does that come from? This is the 30 degree, this is the opposite side, and this is the hypotenuse. So for sine, it's sine of the angle equals opposite sine, unknown, I don't know, opposite side, I don't know what it is yet, divided by 2. Why 2? 2 is the hypotenuse. If I figure that out, I go sine 30 degrees on my calculator, it gives me 0.5. 0.5 times 2 equals opposite, because if I multiply both sides by 2, I can simplify one side, and I end up with this equation, 0.5 times 2 equals opposite. If I resolve that, I end up with 1 equals opposite. And that is my dimension B that we see up here. Again, if I do the side, the A, I end up with cosine of 30 degree equals adjacent over 2. Now, why is that? Well, cosine is adjacent over hypotenuse, and that's what I have here. So if I solve for cos 30, I have 0.866025, which is cosine of 30 degrees times 2, because like I did up here, I'm going to multiply both sides by 2 so that I can eliminate the 2 and get the adjacent side alone by itself there. And if I resolve all this, well, I end up with 1.73205 equals to adjacent, and that is my side A over here. And well, C, I didn't have to figure out because it was a given at 2 millimeters. Now, if this is coming at you a little too quickly, remember we have a video called Trig and Triangles that will help you get up to speed with triangular logic and also basic trigonometry. It's important to do that because in the shop you're going to use trig and triangles a lot. Now, for us, we end up with these dimensions. Are they good? I don't know. I've only figured them out one way, and as I've said many times before, a single calculation isn't necessarily a good calculation. You have to verify everything that you figure out, and not by doing the same thing over and over again. If you do 5 times the same thing, you could very well end up with 5 times the wrong answer. No, you should do it in a different fashion. Now, we've figured out these dimensions with trigonometry. Well, we can verify them with Pythagoras' theorem. Now, for that, we have to know, and that's in the other video as well, that a squared plus b squared equals c squared, and that is true for any right angle triangle. And what that means that the adjacent and opposite sides of a right angle triangle are once squared, so squared plus squared is going to be equal to the hypotenuse, in this case c squared. So a squared plus b squared equals c squared, and generally speaking, c represents the hypotenuse, just so that we always get the right order. If I calculate this out, I end up with 2.9999 plus 1, a squared plus b squared, equals 4. And that equation works out. This is within 1/10,000th of an inch 4, and 4 does equal 4. Now, if I wanted to get technical, and maybe my old math teacher would have said, don't do it that way, he would have preferred that I did it this way and said square root of a squared plus b squared equals c. That would probably be the faster way to do it. But if you end up with something that's equal on both sides, that means that your original calculations here were correct. So let's get over to the lathe and start working on this project. So as you can tell, well, the crank here is going to be quite small. And we're going to use to produce it this piece of square 3/4 inch cold rolled steel. It is quite square and quite accurate. I've measured it and it's to within about 1/1000th of an inch. So this will do just fine. And we're using square stock because we're going to be moving it around in a 4-jaw chuck, and 4 sides will help us to get this accurate. It gives us references that we can rely on for our movement. So we're going to be using a square stock, but what isn't accurate with this is the 2 ends, and one of them, well, I'm going to have to use as a reference to lay out my length positions here. And well, for that I have to surface that in. So we're going to start off here by, well, getting our safety glasses on, and then we're going to rough center this part in the 4-jaw chuck. Just rough center it. Why? Well, because surfacing is a bidimensional operation. It doesn't have to be perfectly centered to be nice and flat and perpendicular. So we're going to rough center it, surface the end, head over to our surface plate, and lay out our lines. Okay, so we're going to want to start by turning that first concentric diameter. I have 3 diameters to turn here, 1 concentric and 2 eccentric diameters. So this first diameter is going to be concentric, and it's going to be 8 millimeters in diameter by 4 millimeters long. And for that, well, I'm going to have to center this part in a 4-jaw chuck. So we'll take a look at that. But before that, I'd like to speak a little bit about the offsetting. I'm going to be offsetting this in my chuck twice, well 3 times actually. Once I'm going to offset, let's say, in the vertical axis this way by 1 millimeter. And that offset will not be touched again. Then I'll offset sideways 1.73 millimeters for the first lobe, and then back to 0 and 1.73 millimeters on the other side for that second eccentric lobe. But my height won't change, I'll just offset it once, but it will slide back and forth here. And well, that could mar or mark my part. For that, here's a little trick, just a mild steel shim that I've cut up into a triangle, and then that just clips right on the end of my 4-jaw. So I only need 2 of these because there's only 2 jaws that are going to hold it in the sense perpendicular to its sliding motion. So let's start by centering the part. And we're going to be centering in the same fashion that we saw how to center a square part in our centering parts in the 4-jaw chuck video. So let's take a look at that. Okay, so I've turned my first lobe and I know where the part is. It's on center. So don't be pulling the part out of there to take a look at it. It is somewhere where we want it to be, and from where we'll be moving our proper offset amount. How much do I want to offset here? Well, one of the axes has to be offset by 1 millimeter and the other by 1.73 millimeters or thereabout. And that means that I'll be moving 39 thousandths of an inch in one axis and about 68 thousandths of an inch in the other. Why thousandths? We were working in millimeters. Well, my lathe here is in inches, and I'm going to be using my cross slide to measure the amount of offset that I'm going to get, or to make sure that I'm offsetting by the proper amount. My cross slide is 1-to-1 ratio, so I'll be moving 1 millimeter in one axis, 39 and 1.73 millimeter in the other, and that's the 0.068 thousandths of an inch, or 68 thousandths, and that'll be my offset. Now, I'm going to set up my indicator on my cross slide. I'm going to come and touch off the part. I'm going to pivot the part slightly to find the low spot on that surface, the surface that I'm touching. Then I'll go a little further in. Then I'll back off. I'll back off till I come back to a 0 or a known 0 on my dial. And I'll say, there, that's the 0 that I want to come back to. Why am I going further and coming back? Well, because I want the looseness or the backlash in the cross slide to be on that side. I don't want to have to change direction while I'm offsetting, because all that backlash is going to come and haunt me. So I'm going to come back to a 0, say that is the 0 where I'm starting, and then, well, I'm going to set my graduated collar to 0 and back off, in the first case, my 39 thousandths of an inch. Then I'll slide my part in the 4-jaw chuck till I come back to the 0 on my readout, and I'll have moved the part quite accurately 39 thousandths of an inch. Now, then I'm going to do the same thing for an adjacent surface to get that second axis offset. But I don't have to start back at 0. I'm already at 39 thousandths of an inch, and I know I want to get to 68 for the second. So all I have to do then is just turn the part, well, ramp off, turn it, come back on, and then move the part to my 68 thousandths of an inch, and I'll have both my offsets. So let's take a look at that. So with the backlash taken care of, I've set up my comparator to 0, and now all I have to do is back up the required amount, which in this case is 39 thousandths of an inch, and then move the part in the 4-jaw chuck so that that first surface, the one that I want to be 39 thousandths of an inch offset, well, comes back to the 0 on the indicator. And well, we're just almost there. And yeah, that's it there. For my adjacent surface, all I have to do is offset the indicator by 29 thousandths of an inch more to get my 68 thousandths of an inch total offset. Now, once I've offset, or I've moved my indicator by the proper amount, all I have to do then is slide the part over in that axis till it comes back to 0, and well, I'll be offset in both directions. And well, there you go. There, my first lobe is cut. Now the second lobe is in the same position, but on the opposite side. The same 1,000th or 1 millimeter, that doesn't change at all, but I have to move the 1.73 millimeter to the other side of the axis of the part. And that is going to be way simpler than what I did in the first for the first lobe, because I'm already where I want to be with the 1 millimeter. and I know where that side is. So all I have to do, the one that I've just cut, all I have to do is come and bring my dial indicator back onto the side that we've just offset, find its 0, ramp off, turn the part 180 degrees, or turn the chuck 180 degrees, come back, and I'll be far away from the part. It's going to be on the other side of the offset. But all I have to do then is move the part in the 4-jaw chuck as to make it come back in contact with my dial indicator to get that same 0 as I had on the other side. And I'll be at the same spot, but opposite to where I was before. Let's do it. Well, the first thing is to find a 0 on my dial indicator. And backlash here isn't a problem, because when I come to move the part in the chuck, well, I won't be moving the dial indicator. So it's going to stay where it is. So I've got my 0, I turned the chuck over and the part 180 degrees, and now I got to move the part in the 4-jaw chuck by sliding it sideways to come back to the 0 that I had originally. And that means that I'll have moved twice the amount that I moved the first time. So the first time I moved 1.73 millimeters, and I've moved twice that, or if you prefer, seeing as I'm working in imperial, twice the 68 thousandths of an inch that I moved the first time. Now, you may have noticed that I've already, pretty well roughed out the second eccentric lobe. Why pretty well roughed out? Well, because I still have a ways to go. But this is as far as I can go with this setup. Because if you can see, the upcoming lobe and the first lobe that I cut, are almost flush. And that means I can't really go any further cutting from this side back. I'm going to have to start cutting from the back towards the lobe. And for that I'm going to have to change my tool. Now you may wonder why I skipped from just one eccentric to this being mostly roughed out. Well, that's a technical reason for that, and that is that I forgot to turn the camera on. If you were wondering why I let the part stick out of the 4-jaw chuck as much as I did, well, now you know. I needed room on the back of the part to work from the back forward, because I knew that I couldn't flip the part over in the 4-jaw chuck to gain access to my second lobe without losing my references. Now I can center the part on the main lobe, the first lobe that I produced, the one that's concentric. It's concentric to itself right now, but I'll be producing a second one on the other end that's going to be concentric to it. So I'll have 2 concentric lobes and 2 offset lobes. Why? Why not? And well, there you go. A nice little twin eccentric crankshaft. So, until we meet again, have fun. Be safe. It's so very important. And happy machining.
So all I ever wanted was a little monkey from you. There you go.